Here at the Printed Electronics USA show, and I'm with lead sponsor NovaCentrix. So this is Stan from NovaCentrix, VP Marketing. Stan, just tell us a few words first about how you're finding the whole printed electronics business over the last 12 months.
In our experience, it's really growing tremendously. I tell people, in fact, in my talk this morning, thank you very much, was a quick mention that we don't see a killer app per se. We see a lot of incremental improvements across a range of industries. And any of the verticals here at the show, which are well represented, wearables, a lot of materials innovation with graphene and a great variety of electrically conductive inks, as well as 3D fabrication, which is a very hot topic now. And you've done a great job of incorporating the printed electronics piece, the materials piece, and the 3D fabrication piece, because they all really merge and come together, don't they, to enable really interesting new applications, and it's really exciting to be a part of that.
Yeah, great. Well, thank you. Well, you've got a really phenomenal stand here with lots going on. So talk us through some of the things on the stand.
Thank you. So we do a lot of things at NovaCentrix.
Yeah.
Because of our company background. We started as a nanomaterials company in 1999.
Right.
We still produce nanomaterials. We make electrically conductive inks, but the focus for our business now is our pulse forge photonic curing equipment. We've seen a tremendous uptake in the acceptance and adoption of those technologies. And in fact, we've had some very exciting production implementations over the last 12 to 18 months, which has been great for NovaCentrix, but also hopefully will have collateral impact throughout the rest of the organizations in printed electronics, and hopefully that will help to buoy the space forward and develop some extended validation throughout that space.
That's great.
So we'll start with our R&D tools. Most of our customers at this point are still R&D. We travel the world to work with customers throughout Europe, Asia, the Americas for sure, and across all of these applications that are represented here at the show. But it's really important for customers when they're working with electrically conductive inks, typically it's a low temperature flexible substrate, to have a way to process and cure those inks, generally at very high temperatures, because that's where they get the best performance and the best value for the money they spent on those inks, whether they're silver, copper, nickel, other materials. They really generally need temperature. And so our pulse forge tools are able to process those materials at high temperatures without damaging the low temperature substrates. So our PulseForge 1200 and PulseForge 1300 represented here are the state-of-the-art for photonic curing, processing of those materials. And the innovation that I'm really excited to be able to share at your show this year is the upgraded power on the PulseForge 1300, which means that we're able to really expand the envelope of materials that we're producing. I'd like to introduce you to our Chief Technical Officer, Dr. Kurt Schroeder, who will take a few minutes to tell us a little bit more about what we're doing here with that.
This is the PulseForge 1300, and we had this here last year. Why are we talking about this again? Well, it's new and improved, bigger and better than ever. It has 40% more power than the previous version, which allows us to be able to cure a lot of materials that we only dreamt of a few years ago. We're talking about ceramics, semiconductors, all cured on very high temperature materials such as glass. Additionally, the types of materials that we've cured, like silver and copper that we introduced several years ago, we can actually get better results with this because of the higher power. A higher power allows us to modulate our beam very much like a laser. So it really is laser processing, except it's about 2 orders of magnitude cheaper. And the nice thing about this is that we try to make the interface, we like to make it fun. So a little bit like your smartphone, we do have a multi-touch display, so it allows us to be able to, just like your smartphone. We also have apps on our operating system, just like your phone, and there will be more to come. So this allows us to do all kinds of interesting things like simulating our process, and we introduced SimPulse a few years ago, and this continues to get better, in which we look at the simulated thermal response of a user-defined thin film stack in response to our PulseForge beam, which might be as many as 15 variables. So you can't keep track of this in your head, you have to rely upon the simulation. In addition to this, we have automatic logging of all the conditions and automatic retrieval. You can look at process conditions from a few months ago and instantly load them up and process again. We can change the settings on the machine to make them user-defined, customized, just like your smartphone. We also have automated calibration, which you don't have to remember what your settings were. It actually does it for you and automatically compensates in order to have results that are precise and also repeatable. Now, when we do this, of course, we always have to have a tie to the industrial system. Anything we do here has to have a link to the industrial system. We prefer to do it via software because that's actually traceable. Often we're working with people on multiple continents that have speak different languages, but this is the great equalizer. It allows people to have one common language for all the users. People using Simpulse, for example, on the cloud, or in an R&D setting, or in production, they all speak the same language. Now, in order to translate this to an actual production setting, we have some additional hardware on top of the higher power. We have an integrated environmental vacuum chuck that allows us to be able to process material and control the boundary conditions. To make a long story short, we can heat things, we can cool things, we can put things in a controlled atmosphere, we can put things in a reactive atmosphere. All things that one would do industrially, we can do in an R&D setting so that we eliminate any basically risk. We mitigate risk with this technology. So with that, I'm going to let you go to the next setting, but this machine is horribly helpful to us, and it allows us to be able to predict what will happen in an industrial system.
Thanks, Kurt. So we're super excited about the capabilities here. Our customers are excited about the capabilities. And the whole reason that we spent the investment to develop this upgrade is because of the applications, as Kurt mentioned, in semiconductor processing, transparent conductive oxide processing, and other applications that require a very sharp thermal gradient and very high process temperatures. So this is our collection of R&D oriented tools. As we come further into the exhibition area, we're going to see an example
touch control
of a scaled production with process. So it's really important that our customers that work on the 1000 series tools have exactly a pathway to production, right? So that the process conditions that they invest time and money on the R&D setting can be absolutely applied to production. So this is a gantry for a production width tool. Here we have the lid open so we can see that it's a super clean design. This particular set, right? So these are the lamp units that power that deliver the optical energy into the system. So we can close the lid,
and that's the width of the web. You have
exactly right. Thank you, Raghu. Yeah. So the material would be running along underneath this. So this is across the width of the web. We can, by adding lamps, we can go beyond 4 meters in width. So it's absolutely scaled for large generation display processing. This can be applied to web processing, sheets such as for displays. And these units are in production now in factories throughout primarily Asia. So it's as I mentioned, it's an exciting time as these technologies move all the way through the product development cycle into production. But there are some steps that happen in between the small scale, single lamp R&D processing and this absolutely full scale factory. And so one of our other really important product releases this year is this transitional scale roll-to-roll processing tool. So to talk a little bit more about this, I'd like to introduce Ian Rawson, who's the Senior Applications Engineer for us, and he's been instrumental in this particular program.
Howdy. So this is our PulseForge 1200, and what we've done is we've actually applied it onto a roll-to-roll unwind system, right? So actually what we're going to do here is a start-to-finish production of printed electronics. We're using a Harper QD flexographic press, which, if you're not familiar with flexograph, is really nothing more than a rubber stamper fed by an analog which meters the ink against this dark blade knife. Next thing we go over after the print is made, it's a little bit wet. So it's actually dried out by an ADFOS near IR system, and it just applies infrared light, removes the solvents, and we have kind of like a green state. It needs to be centered together. So over here we have the PulseForge 1200, and what that does is applies a flash of light to actually center the metal nanoparticles together. So we're going to spool it up, and what you're going to see is the whole process start to finish.
whenever we operate this at the event, we did a scheduled demo cycle throughout the last couple of days. People immediately appear to watch it, which is really exciting because it's validating for us that we're doing something that that has interest and has application here at the event. But as we go around the further booth space, I do want to highlight a couple of more technical topics, which is as we look at flash lamp processing, it's really important to maintain a uniform exposure intensity across the width of the flash lamp as we look at the web width. When we do this, it allows for improved processing speed, we get better uniformity, and the uniform processing ultimately leads to a higher quality final product. This is really an important concept for the production users, where the quality assurance managers and the quality control inspectors are looking to maximize yields, maximize product quality, and they're really tracking their statistical process control charts for the performance of their materials. Folks that don't take the care in establishing a uniform pulse profile, as they start to stack these profiles together to process larger material sizes, larger sample sizes, then they wind up with these bigger and more dramatic irregularities in the pulse intensities, and that causes big quality problems. And when you have that kind of a circumstance, when we look at an actual application like this RFID antenna, what we see here is we see incredible uniformity. We could measure the actual sample and see that sample to sample to sample, the repeatability is within a fraction of a percent. But also visually, we can just do a quick quantitative check, and the quality of the image is quite uniform. This is an application that we're doing with Mollbauer for RFID production. They're based in Germany. They're the industry leader in RFID manufacturing equipment. They came to us and asked if we would help them in releasing the next generation of RFID manufacturing capability. Of course, we're glad to help. So we worked with them on providing our copper oxide electrically conductive ink that prints as non-conductive, really inexpensive copper oxide on paper. And then our PulseForge tools apply the photonic curing concept, convert the copper oxide into copper with the reduction process, and we have a really highly conductive, high performance, highly durable RFID material for paper that's, as I said, very low cost. So we talked earlier about the role of SimPulse. Kurt indicated that SimPulse as a numerical simulation is really important, not just for helping to understand the thermal response in materials that are being processed, but then also to use as a design tool for engineers that are working in the print electronics space. So I'd like to introduce you to Dr. Rick Zoomstag, who's going to talk to us a little bit more about the SimPulse that we're showing here at the conference today.
Okay, what I'm showing here is actually it's the software that comes with every instrument. And so you'll see there's a control panel where we can adjust the amplitude of the pulse length. But included in this, well, actually, there's if we have a bolometer that can measure the energy for the pulse, that's included here. But the important thing that I want to talk about is the simulation that allows us to model the structure, so we can create a stack of materials. Right here, I'm showing that we have a silver layer coated on a PET layer. And if you look here, you can see that the top surface with these pulse conditions we have here reaches 500 degrees C. The bottom surface barely gets heated. And that's one of the real secrets of PulseForge, is that we can create a thermal gradient from top to bottom that allows us to take a material that might require going to 500 degrees, coated on a temperature-sensitive substrate, and most of this temperature-sensitive substrate never gets heated. So if you look at the blue line here, you will see that as I move this down, this is showing exactly what the temperature is through this stack at every given level. And you can see that only going down 20 microns or so, the temperature never reaches more than a third of what the maximum is. And that's the real special feature of PulseForge, in that it allows the substrate to act as the stabilizing agent. And so that allows us to process something at high temperatures on a temperature sensitive substrate without that substrate distorting, so you can run it through a web. You don't have, it provides the image stability that you need to make a quality product.
So there are many different material formulations. How do you take that into account in the simulation?
Okay, the software allows us to pick many different things where we have thermal properties incorporated into the data feed. So we can pick a lot of different materials like amorphous silicon coated on there, and we immediately see the change in the temperature profiles. We can change what the polymer is very easily by simply going through here, and I might I'm trying to find the right polymer. Well, let's just say pick soda lime glass. And actually what you saw very quickly here was that when I use soda lime glass as a substrate, the glass is a much more conductive material, thermally conductive material than the polymer was, and so the total temperature, the maximum temperature you could reach was much lower, because that was allowing more heat to come out of the top layer during the course of the pulse.
So thanks, Rick. This is a key tool for us, and we really emphasize that. This is a tool not just for early users, but also definitely for advanced users. So part of our philosophy is, at NovaCentrix is a recognition that this is a team effort to be successful in print electronics, and that's not just a team at NovaCentrix, but also an external team. So we certainly value working with Raghu at IDTechEx, so thank you very much. And then also with other companies and organizations. So at IDTechEx, we always try to pick a couple of collaborations that have been especially crucial for us for the previous year and for the coming period of time. We'll go around the corner here, and I'll introduce you to our really exciting equipment release. I'd like to introduce you to Dr. Ken Church, founder and CEO of NScripts, based in Orlando, Florida. Ken is really a savvy veteran in the print electronics space, one of the early folks working on the DARPA origins of printed electronics, and we're super excited that we've been able to collaborate with him through the FlexTech Alliance, an association here in the U.S. And this particular project was also sponsored by Army Research Lab, so we had a customer for this even before it was completed. NovaCentrix and NScripts both invested fairly considerable resources internally to bring this to fruition, and I'll let Ken talk about what this incredible machine is doing and why we're working on this.
Great. Thanks so much. I appreciate it. This is actually very exciting, because not just because of what we've been doing, but what we're doing together. We can see back here just a little bit, there is a 3D printing piece of equipment, and this is not just about 3D printing. This is about multiple heads doing multiple things. And so one of the exciting things about this is, if you can imagine really and truly starting from nothing, and everybody talks about going from art to part, it's a really big buzzword. But this in and of itself is truly one of the first systems that really has the chance to go, as they say, from art to part. But there was something missing, and that's what was really exciting about this, and why our relationship with NovaCentrix became really important. Because we print, and there's a number of materials that we will print, from the plastics all the way up to a number of different electronic type materials. Just as Stan has said, the printed electronic materials, and those have been there. But one of the things that you will always do is you'll always post-process. And the way they do that in industry today, they post-process, they will simply take that and they'll put it in an oven, and then it sits there for a very long time. But what if you could do something different to replace that post-process, and you could in situ, after you build, you flash, you cure, whatever that you have to do, you center, and from that, a working part comes out. Truly from art to part. And that's really where we're standing. And so what you'll see is really the mechanism that allows us to print with the kind of resolution that's going to rival what's going on in state of the art. The smallest resolution that we print is 12.5 microns from a thermoplastic point of view. So the resolution is there. And then the kinds of resolutions that you might want from the printed electronic side, where we're printing 50 microns or 100 micron wide lines, but putting all those together in a structural manner. want you guys to remember a term, if you would. Everybody understands printed circuit boards, but what about printed circuit structures? A PCS is going to be a new buzz that's going to come out, and printed circuit structures are not going to happen unless you have a complete process. In situ post-process is a critical part of this thing, and that's really what we in NovaCentrix have been doing and doing well together. So we're excited about the launch of this thing, we're excited about where this is going, and eventually what you're going to see is not just us at trade shows like this, you're going to see this in home, you're going to see this in your pocket. Your pocket's a great one. I want to take this out of my pocket here. This is a printed phased array antenna element. Antenna on the back, a massive amount of electronics that's going to happen in here, and it is 3D printed. And what is exciting about this is as you start building these things, who can touch it? Well, these things are literally tens of thousands of dollars. Your everyday guy's not going to touch it. If you don't know what a PAA is and you're concerned about what that might be or how it might affect you, your government uses every day to protect you. But these are very expensive processes. Can you imagine this coming out instead of being tens of thousands, maybe $100 or hundreds of dollars? This is what this is going to enable. We understand the implications of what's in front of us, and we're excited about that. Thank you so much for the opportunity. So I want to thank NovaCentrix as well. They've been very generous in their collaboration with us, and we're looking forward to a great partnership with them.
We certainly appreciate it. And this is a great example. There's so many value propositions that can come from marrying these technologies together. Ken's group has been very involved in developing his technologies. We've put tremendous investment into ours, and when they come together, it really can enable incredible products, in this case potentially some tax dollar saving efforts as well, and so we definitely appreciate that. Thanks Ken. So let's continue on around. Some other collaborations that are important for us. We've done and continue to do a tremendous amount of work in Asia. So we've collaborated with materials companies. ANP provides an excellent set of inks based in Korea. Here we have Showa Denko, which is a key Japanese materials partner with us. They're doing some really breakthrough work with silver nanowires and some silver copper composite inks as well. This is a tremendous relationship that goes back a few years, and together with their materials and chemicals expertise, along with our chemicals and materials expertise and our expertise in the processing equipment, it's been really a successful venture. Here's the new relationship. Hitachi High-Tech is commonly affiliated in this case with semiconductor manufacturing equipment. We're launching a new collaboration with them to do integration of our post-processing tools into their ability to build complex multi-step production processes. This is a great collaboration of our technology and our product know-how with their technical capabilities and their access to existing and new markets in Asia and then throughout the world as well. So as we come back on around, this really is an exciting time for NovaCentrix. It's an exciting time for printed electronics in general. Ragu's event here at the IDTechEx Printed Electronics USA in 2015 is our #1 stop, certainly in the US, where we can showcase new innovations and new products for us. I'd like to thank Ragu and his team for our support.
Thanks.
And we will definitely see everybody next year in 2016.